Welcome back YouTube to the ASX Portfolio channel. Today we're going to be talking about Monte Carlo simulation. So as you can see in the top right screen, this is what we're going to be doing today. We're going to be making a simulation of portfolio out to 100 days, and we're going to track that over time. So we're going to be implementing in Python. I hope you guys really enjoy. So what is Monte Carlo simulation and why would you want to do it? So the Monte Carlo method is most generally described as a computational simulation that relies on repeated random sampling to obtain numerical results. So that's a bit of a mouthful. Let's try and understand why we'd want to do this first. So in solving problems, we often rely on random variables that have some kind of underlying distribution. Now, depending on the problem that we're trying to solve and the random variable and their distributions, there may or may not be a deterministic solution. So what I mean by this, in other words, if you were to place the same input into our deterministic algorithm, you would always get the same output. However, in practice, as we start introducing more complex random variables to our models with different underlying distributions, this becomes a challenge, working with the non-normal multivariate distributions and working out an exact mathematical solution. So instead, in practice, we rely on a method, Monte Carlo simulation. As we increase the number of simulations and therefore how many samples we're taking from these underlying distributions, we hope to try and converge on an exact solution. So hopefully you guys enjoy it. Let's jump into the code. So jumping into the code, first thing we're going to do is import our dependencies. So first thing, let's import pandas. So we're going to need to import numpy. We're going to need matplotlib to graph stuff.pyplot as plt. We're going to import datetime as dt. And the other thing we're going to need to import is pandas data reader. Okay, so from pandas data reader, we're going to import data as PDR. Now, that is a module where we can get Yahoo specific data. So just pip install that and we should be good to go. So let's import data. We're going to define a function called getData, and that's going to be stocks, start date and end date. So what we need to return is a covariance matrix, and we need to return the mean returns for whatever stocks we put in there for a certain date range. So first thing we're going to do is go stock data pdr dot get data, and we're going to choose Yahoo. So that takes in stocks, a start date and an end date. So the next thing we're going to define is we get a data frame back, and it has a whole bunch of information, bid ask, close prices. We're going to only choose the column that says close prices for that information. We're only interested in the daily changes. So the returns of this matrix, we're going to get the stock data and use the inbuilt pandas function %change to get the daily changes. We're going to use this returns function to compute the mean returns and the covariance matrix. So mean and returns.mean, and we're going to go covariance matrix, which is returns.cov. So let's return the mean returns and the covariance matrix. Great, so let's define our stocks. So stock list. We can just enter a whole bunch of ASX random stock quotes that we know, Telstra, NAB Westpac, and let's go Santos. So because I know the format of the Yahoo data list, we're going to use list comprehension to add, so stock for stock in stock list, we're going to add the string .ax, because Yahoo requires .ax at the end of all Australian stocks when we're pulling it in that data frame. So we also need to define a start date, which is going to be, well, let's define the end date first, which is going to be dt.datetime_now. .now, and then the start date is going to be a shift from that end date, so dt.time delta, and let's call that days 300. And that time range that we're specifying there is very important for how we're computing that covariance matrix, because it's the covariance matrix that makes the world of difference when we're taking into this Monte Carlo simulation. So the parameters derived there are very important. Let's test this function. So mean returns covariance matrix equals get data, stocks, start date, end date. Cool. So let's print mean returns and let's see if that works. So Python activate base, Python MC, excellent, and you can see that we've returned our mean returns there. So now that we have our data, let's define weights for the portfolio. So weights for the portfolio, let's just define them randomly. .random, and the length is going to be that mean returns column there. I think I'm just able to do that. So random is going to get a number between 0 and 1, I believe. 0 and 1, so we need all of those to sum up equally to 1. So mp.sum. So we just need to normalize by the sum of all those weights to get the weights matrix equal to 1. So let's just print weights to see that we're doing the right thing there. So once we have that, now we'll be able to go into our Monte Carlo simulation methodology. That looks good to me. So note the size, it's a 1 by whatever our number of stocks is as an array. Let's jump into the Monte Carlo simulation, Monte Carlo method. So first thing we're going to define is the number of simulations. So MC sims, let's call that 100 at the start. We're also going to define the time range, which is going to be 100 days. Time frame in days. We need to now, before we go into our big loop, where we're going to say for m in range 0 to MC sims, you know, we're gonna do stuff. We're going to do our Monte Carlo simulation. MC loops, we need to define some empty arrays that we're going to store information and retrieve information from. So one of these arrays is going to be mean returns in the format of the number of days. So for that, we're going to call this mean matrix, and we're going to use np full. Now np full takes a shape and it takes what we're going to fill it with, so the fill value. So the fill value, as you probably guessed, is going to be the mean returns. What we need to do is put this in the shape of our variables here, so the t. So it needs to take into consideration how many stocks we've got and the number of days. So because of the way this fill value works, we've got to define it by number of days, and then secondly, the length. Let's use that weights vector to define how many variables, how many stocks are in the list. So it fills this based on the mean returns. Later on, you're going to see that we're actually going to need to take the transpose of this matrix in order to do the computation below. So just take that for granted for now. The other array is the array that we're going to store all this information in. So we're going to call that the portfolio sims matrix. And that's just going to be np full shape with fill value, and we're going to go 0.0 so that there's floats. Floats can be added. If we went 0, then only integer values can be added to this simulation. And yeah, we need floats. So the shape value is going to be some factor of the number of sims and time. And in this example, we're using time first and MC sims for the dimensions. So just an empty array with a number of sims and time frames. So as we run through this iteration, we need to use the formula to be able to work out daily returns. Now I'm just going to chuck the formula up on the screen here. You can see daily returns is the mean plus by the lower triangle from a 𝐎𝐵𝐻𝑒 decomposition, and this represents the covariance matrix. So you can look up 𝐎𝐵𝐻𝑒 decomposition to find that lower triangle. It's just a way of representing it in this form. We're going to use it because it's very simple for Monte Carlo analysis with stocks. When we assume that we have a multivariate normal distribution, we can use the 𝐎𝐵𝐻𝑒 decomposition to easily represent the daily returns by that formula. So we're taking a whole bunch of uncorrelated sample data that we sample from the normal distribution, and we're correlating them with the covariance matrix through the use of this lower triangle L. So let's just jump into it. So we're going to sample a whole bunch of uncorrelated variables, mp.random.normal distribution, and the size of this is going to be important, and that's going to affect the number that we have there. We're going to want this in T with the number of stocks, so length, weights. Excellent. So that'll give us T times the number of stocks that we have, uncorrelated random variables from the normal distribution. Now we're going to work out what that lower triangle is, NP linear algebra module from NumPy and Kovsky, and we're going to give it the covariance matrix. So very simple, it's just going to work out what the lower triangle is for a Kovsky decomposition. So as we have in the formula there, we're going to just say the mean, the daily returns are the mean returns there, so mean M matrix for all those values of T, plus the inner product, because we have a variable number of lengths here. So the inner product, so the dot product between all these different stocks in the portfolio. And we're going to have the lower with Z. So let's make sure the dimensionality lines up here. This is the number of stocks by the number of stocks, and this shape is T with weights with the number of stocks. So that should work out there. And the mean value is, it was T by the number of stocks, but we transformed it to be the number of stocks by T. And the reason we didn't just switch that beforehand was because the field value associates with this second quantity here. Okay, so let's take it that works. What we need to do is now record those portfolio daily returns and accumulate them across days. And then of course we want to save down this information per simulation. So for all the days t, for the specific simulation m, we want to take the cumulative prod. So returns the cumulative product of all the elements in this series. So we're going to take the inner product again of the weights matrix and the daily returns. And for the daily returns, I think that's going to have to be the transpose. Yeah, so here we're just evaluating what the portfolio is for each day, and we're taking the accumulated product of daily returns so that we don't have daily returns going out for the entire time series, but we have the cumulative effect of those daily changes. What we're going to do is add a initial portfolio value. Initial portfolio, let's say we started with $10,000. We're going to add 1 because we have daily changes here. So let's add 1 and start off at the initial portfolio value. So let's plot portfolio sims. Let's just check that runs first. And we'll add some things to this graph, a Y label, which we call portfolio value. So we didn't get any error messages, which is good, but the plot didn't show up because I didn't say plt.show. So we've got days on the x-axis, and the title is going to be MC simulation of a portfolio, a stock portfolio. plt.show. So now if we run that, we should get our nice image of our returns from initial portfolio $10,000. So as you can see, we've now got our image here of from $10,000, all our simulated variables of correlated assets between them, as defined by our covariance matrix. So again, the covariance matrix and the time period that we parameterize that over is extremely important. So you can play around now with the number of simulations that you take here, the time frame, and of course the components of stocks that you have and the time range. So please enjoy using this Monte Carlo simulation, and I hope you get a lot of value out of it. Thank you very much for listening to ASX Portfolio, and see you guys in the next one. Don't forget to like and subscribe if you want to see more content like this. Cheers.